Good afternoon. Thank you for joining the SCA webinar with Dr. Julia Wellner on the Upper Texas Coast as a reservoir analog. Before we start today's webinar, we'd like to ask a few questions about the demographics of the audience. So I will be sharing some polling questions. And I'm launching the first poll now. What is your primary discipline? And I'm getting some responses. Looks like we have some geoscientists in the audience, some petroleum engineers, some in the other category. So you'll find the poll on your screen now. Please vote for the discipline that you're in. Like half of you have voted, so I'll give it a few more seconds. And so I'll go ahead and close this first poll. Looks like we've got a good number of geoscientists in our audience today and some petroleum engineers and some of the other category. So the next polling question I'll ask is, how many years of full-time experience you have? Okay, so that one isn't coming up for me, but you can certainly give me your years of full-time experience in the question or chat box, and we'll look at that as we go. I'm going to go ahead and hide the polling and share my current screen to introduce our speaker today. Okay, so the question has come up for full-time experience. If you want to share your full-time experience, a few of you have voted in that area, so please go ahead and vote. I'll give you a few seconds to do that. We have several people with more than 30 years, and it looks like the results are still coming in. I'll go ahead and close that poll now. And now I will introduce our speaker today. So Dr. Julia Wellner will be presenting the Upper Coast as reservoir analog. And Dr. Wellner is a marine geologist at U of H. She has degrees from Bryn Mawr, University of Alabama, and Rice. And she's been working at Rice and U of H in the Department of Earth Science. She's now associate professor in the Department of Earth and Atmospheric Sciences. And her primary research is Antarctic glacial history and marine geology. She's just returned from a trip to Antarctica, and she also has experience in the Gulf of Mexico and Texas Gulf Coast that she'll be sharing with us today. And Dr. Wellner teaches a class that's offered as a field trip, one-day field trip in September through SCA on modern coastal systems of Texas. And so you can make plans to attend that now if you're interested. In addition to today's webinar, we have another webinar offered in May with Dr. Lee Richards talking about drilling mud. Why is my mud bill so high? So be sure and register to attend that as well. And so without further ado, I'm going to turn over presentation rights to Dr. Wellner. And Dr. Wellner, please take it away.
Sure. Good morning, everybody, or good afternoon. And thank you for logging in today. I'm happy to be presenting to you. I'm sure all of you, like I have attended lots of online meetings recently. This is actually my first time, though, ever giving a lecture like this online. So I'm happy to be doing that with you, and just let me know in the chat function, or let Susan know if there's any issues with this first time lecture. Lots of things have been going online, including classes. This is actually an extra step, not just moving classes online, but moving a field trip online. It's one thing to try to do a class remotely. I think it's even harder to explain what we might do in the field by this remote connection. But that's our goal today. And I'm going to get started with a series of slides. Do you now see my title slide? Okay.
Yes, we do.
Okay, great. So what I'm going to talk to you about today is the area of the upper Texas coast that's pretty close to Houston, the section from the Brazos River to Galveston Island. We're really focused on modern sediment transportation, but we study these modern systems to understand how they serve as analogs for reservoirs, and along with that, for seals or other parts of the overall petroleum system. Working in the modern gives us great opportunities because we can see so much more detail than you might be able to in the subsurface. And in addition, we know what the current conditions are. We know how the water is moving or what the drainage basin is like. And so modern systems give an opportunity to get detail that is not available elsewhere. And that's what I'll hope to show you today. So the outline that I'm going to present is just a little bit of the database to show that this is not just walking along the beach, but a true research endeavor with a great deal of background data supporting it. And then I'll step through just a short overview of the region. And then I've picked one of our field trip stops, the Brazos Delta, and we'll focus on the details of what's visible there at the Delta. And then just a sneak peek at our newest research area and recently added field trip stop at the San Luis Pass Tidal Delta. And then at the end, we'll have some time for questions, which you can enter into the chat function. So the database that I am relying on is extensive, and it covers both onshore and offshore data. The image that I'm showing here is the Rice University Gulf of Mexico database for seismic and platform borings. In the introduction, Susan mentioned that I was a Rice student for graduate studies, and I began this work there working with John Anderson. And so a lot of the work that you're going to see, the older materials, all come from that Rice University project that was supported by an industry consortium over many years. The newer work, the field trip stop at the Brazos Delta, and then the brand new one at the San Luis Pass Delta, that's work that my students and I are now doing at the University of Houston. So the grid of seismic that we're relying on for this upper Texas study runs from the Texas-Louisiana border down to central Texas, in this particular image showing towards Matagorda Bay. And then the seismic data goes all the way from very close to the shoreline out to the shelf break. Most of this is collected by students. Some of it is industry donated. The offshore seismic that was collected by Rice University was collected on a modified fishing boat called the RV Lone Star that was able to collect seismic and do shallow coring as well. The students did all of this work themselves offshore. And so this is low resolution data in the sense of industry data. On the other hand, it is plenty high resolution to see the shallow sediments. all of that data is stored and archived. The cores shown here are sediment cores that have been collected on various field excursions. Because these are sediment cores, not rock, they are kept in a walk-in core cooler, refrigerated. And sometimes we bring these samples or posters out in the field with us. So here you can see me teaching on a field trip, much like the one I lead for SCA, where students come out in the field. We look at the database materials and posters and guidebooks, but do so out on location in the setting where the data was collected to help put it into context. My students and I at the University of Houston are continuing to do this research. We are now collecting CHIRP, or very high resolution 2D seismic data, as well as seafloor samples that we look at grain size and smear slide data. And then we also use publicly available cores and databases such as TextSed. So how do we collect CHIRP data? This looks very low tech, but this is a modified party boat. It has a davit and some tow points added, as well as a reinforced bottom, so that we can tow seismic equipment in shallow water. This low-tech party boat is actually the perfect tool for working in the very shallow water, not even out in the Gulf, but in the bays where the modern deposition is happening. We also collect sediment samples in even shallower water than we can go with the pontoon boat. So we collect these sediment samples using kayaks, although often we actually walk through the delta and tow the kayak, and the kayak itself just serves to as our pack horse, essentially. Our sediment samples and other equipment are in the kayak as we walk through the delta. On projects like this, we're doing things like studying the water depth, details of ripple height, ripple wavelength, the geometry of individual ripples and bars, how are the bars moving, and then all of that builds up into a database that allows us to think about how these modern deposits are forming. Here you can see my students working offshore, and this is our little vessel logo for the RV Mishi Peshu, which is a water cougar. So what I'm going to do now is talk a little bit about the upper Texas coast in general and show you the broader context for each of the field trip stops. This broad context will show some of the regional geology. It shows that we're putting all of this sedimentology that we're doing in the field, putting it into a sequence stratigraphic context. My primary job is teaching things like sequence stratigraphy to graduate students. And so all of this detailed sedimentology is put into that context. This part of the talk is largely based on the work of John Anderson and others at Rice, summarized in an SEPM special publication in 2004, as well as many other published resources that are available. So the study area that we're broadly talking about is all of the upper Gulf Shelf, running from the US-Mexico border around to Florida. And what this image is here to show us is just how the Mississippi River, which is the area shown in gray, is really dominating anything that we will see on the Gulf of Mexico shelf. We're going to be looking at our first section at the Brazos River, which in this image is shown in light blue. And that's the largest river solely in Texas. Well, it has its headwaters in New Mexico, but not significantly. It's not the most sediment of any river in Texas. but it's still dwarfed by about 2 orders of magnitude by the Mississippi River. You can see out here that the shelf along Texas is sort of a medium width shelf where we're looking at the Brazos River, and that's going to control how sediments are distributed throughout the rise and fall of sea level. The sea level history that we're thinking about is a complete glacial eustatic cycle, meaning we go through the high stand, low stand, and transgressive systems tracts, just like you would in the Cretaceous or the Eocene, any other section of geologic history. We have a full glacial eustatic sea level cycle, but it's happening very quickly. And so this is an image, a composite of many different papers, which are summarized here. And on the x-axis, we have time going from 0 or to today back to 140,000 years ago. So working in coastal systems like this, we're usually not thinking about millions of years. Even if we're going far back into our data set, it's just about 100 to 150,000 years ago. But because sea level goes up and down so quickly during the sort of last 2 or 3 million years, this last 100,000 years gives us a full glacial cycle. On the y-axis, we have sea level, and again, 0 or today is here. And then as we go down this axis, we go down to about negative 140 meters. So this is the lower part of sea level. And then there are times when sea level is higher than today as well. And so if we look through this diagram, what we can see is that from about 125,000 years ago or so, that was the beginning of the last high stand systems tract. And sea level fell for about 100,000 years, reaching the last low stand of sea level down here around 20,000 years ago. At that time, sea level was about minus 120 meters lower than it is today, meaning that for many places it was below the shelf break, and we got full incision and development of a sequence boundary. Sea level then rose from that low stand position, forming the transgressive systems tract. And then some people would say we're still in the transgressive systems tract. Sometimes we say we're now into the very beginning of the new high stand. That's a debate we could have some other time. But what we see is that in this time period, we go through a full cycle of fall, low, and rise, even though we're only looking back 100,000 years or so. Summarized in a seismic section across the Texas shelf, we can see whited out here is just the water surface. And the systems tracts, or the surfaces that we're going to talk about, are the stage 2 sequence boundary shown here. That's the last low stand, the most recent sequence boundary 20,000 years ago, shown here in red. And then the stage 5, or maximum flooding surface, that formed the last time sea level was around where it is today. This stage 5 maximum flooding surface in this image is shown in yellow, and it's from around 120,000 years ago, like I showed on the last figure. And then you can go down and those cycles repeat themselves just like they should in sequence stratigraphy. So using those two main surfaces, the red sequence boundary and the yellow maximum flooding surface, we can build a series of images. But it's not just based on seismic. We've got seismic, core, timing, in this particular case from radiocarbon dates, and then sea level records from known composites, from forams, etc. So we are tying the work from the seismic, shown here is the pink sequence boundary, and then we can tie that to parts of the core, which tie to individual foraminiferal records. Putting all of that together, what a series of students have done is make these maps showing what the region looked like. So here, for context, this is Galveston Bay right here. So Texas, or excuse me, Houston would be sitting right up here at the head of Galveston Bay. In the gray to right boundary is the modern day shoreline. And in the black dashed line is the approximate position of that last Highstand shoreline. Sea level was around +5 or +7 meters compared to today. And so the shoreline was farther inland than we see it today. At that time, the Brazos Delta made this large multi-lobe delta that expanded out from where we see the Brazos River today, and then these lobes prograded out towards the shelf. This delta during its early Highstand is surrounded by a mud blanket, similar to the one we see today in the central Texas shelf. By the late Highstand, so as sea level continued to prograde out to the shelf break, the Brazos River, and if we focus on the Brazos, because that's our field trip stop I'm talking about, the Brazos River continued to prograde out towards the shelf break. But because it had already made those large delta lobes before in its early Highstand, it continued to incise across its own lobes before it reached the shelf break, so that the late Highstand is incising the early Highstand lobes here. Because we have a relatively shallow shelf break in this area of Texas, by the time we reach the low stand here, the shelf break delta, the shelf margin delta is starting to form. We have this sediment that is coming out here off the shelf and moving into deep water. This is just an example seismic line or pair of seismic lines from this section of the shelf, showing how the Brazos Delta formed over time. In part, it's just nicer to show you some prettier seismic than I started with. And what we can see if we move from the inner part of the shelf out towards deeper water, we can see those same surfaces. And here you see that great image of here's the older delta lobe prograding out across the shelf, reaching the shelf break by the late Highstand. And then we have that sequence boundary from the river incising across its own deposits. By the time we reach the low stand systems tract proper, then we see that these rivers not only made it all the way out to the shelf break, but they have merged. And rather than individual drainage valleys, the Brazos, the Trinity, the Sabine, which is the Texas-Louisiana border, each of these rivers have merged into these massive valleys, bringing sediment out across the shelf break. These images here, of course, are just cartoons highlighting the main environments, but there's also much more detailed mapping of each of these surfaces here in a summarized figure by Alex Sims and others, where we see how that sequence boundary came out and the ruggedness of it as it reaches the shelf break. As sea level started to rise, following the low stand, sea level rose. Of course, all of these systems then stepped back towards the modern day shoreline. As water came across the shelf, all of the environments moved with it. But of course, they don't follow the exact same pattern. We have these much smaller lobes as sea level moved onshore. That's very standard wherever you're working, because the sea level changes so quickly during the transgressive compared to the falling Highstand. The systems don't develop those large lobes, but rather we can look and see these small lobes move very quickly towards the land. And then we can look at the modern environments where we know what we see today We have bayhead deltas, bars, estuaries, tidal deltas, and that's what we're going to focus on now, what we can actually see. And we're moving now from this sort of showing you this, what counts in this work for long-term, 100,000 years. That's the background. Now we're going to move in and talk about these places that we can see and how they fit into that context. I forgot about this slide. So the parts of the Texas coast are very different from the other parts of the Gulf Coast. So if we look just at how the system's tracts are shaped, these are cartoons showing that. And we can see that West Florida, for example, has this very broad distribution, ramp setting, and that's quite different to how we have Central Texas with a very narrow, steep shelf. And then you get into what we have here for the Brazos River, all the way from the Trinity through East Texas and Brazos. We have this broad area, but it's a very low gradient shelf with moderate subsidence and these small suspended load rivers. And that matters because we're going to really be thinking about suspended load sediments today. Okay, so now what I was saying is we're getting towards our case study. So this is going to be emphasizing one of our field trip stops. And moving into this section is largely based on the MS thesis of one of my students, Derek Rice, who focused his study on the modern Brazos Delta. So this is just another reminder of how to think about the region that we're looking at. This is what I think is a beautiful image from the U.S. Geological Survey, putting the drainage basins of all rivers in the U.S. onto one image, just in different colors. And of course, here you see the Mississippi, and I talked before about how it just swamps and dominates anything we're looking at. And then here in this darker pink color, this is the Brazos River. So that's the one we're going to be talking about. And you can see that it is the largest system between the Mississippi and the Rio Grande. As we look at the Brazos Delta, now here's that drainage basin shown here on a map of Texas with just that little bit in New Mexico. And here's a Google Earth image showing the modern Brazos River as it enters into the Gulf of Mexico. We're going to step through a few different details about this delta, but just starting off, I think you can see here that this side is different than this side. We can see these scroll bars through this lobe. So a few points stand out right away as we look at this delta. The database that my student Derek used to complete this work includes 20 offshore cores. These were all collected by Rice University and then given to us for this work. We're using core descriptions, grain size analysis, and also X-ray diffraction. I'm going to show you why that X-ray data matters so much here. Oops. There we go. So the background previous studies of this area include 3 key points. First is a paper by Tony Rodriguer and others studying how the delta evolved. You've likely heard me say a few times now, the modern Brazos Delta. It is important to call it the modern delta because it's actually only been there since 1929. The older delta is right here. This is the area near Freeport or Surfside Beach. And this area had industry and served as a harbor even prior to 1929. And the ships were starting to have a hard time getting in there because of the sedimentation. So in 1929, the US Army Corps of Engineers diverted the Brazos about 10 miles in this direction down Longshore Drift. And so we know so much about this delta because we know exactly the year it started. And so this paper by Rodriguer and others gives the detailed evolution through a series of aerial photos from 1930 moving forward. Another thing that we know about this delta is from a paper by Bhattacharya and Giosan from 2003, who were on a field trip standing right here, just like we go on our field trip, standing there and observed how asymmetric the delta was. Well, it's not really surprising. It's a delta in a longshore drift environment. But this delta helped inspire some of this model to explain how two different delta lobes can develop, or two different sides of a developed delta are so different. Now, in this case, we already knew the role of longshore drift here because this delta actually grew from 1930 through to around 2000 or so, much more quickly than the sediment yield would suggest it should. And that is because it was cannibalizing its old delta. Its old delta that was up here somewhere was being eroded and feeding its sediment into here. And so this paper helped explain this asymmetry through the role of longshore drift. And finally, a very nice paper by Carmen Fraticell in 2006 examined the individual bars in this delta lobe and was able to suggest individual dates for each of these higher parts or ridges within this lobe, so that we have a 1992 ridge, a 1965 ridge, and so on, where we get individual ridges or episodic growth in this delta. This is going to come back up later in the talk, but what we know is that along with this same periodicity or episodic nature is that we have flood cycles across Texas that also correlate to this timing. So here's another image of the modern Brazos Delta. Again, here's where the river comes out today. This nice channel that you see through there, that's the Intracoastal Canal. So that's an artificial shipping navigational channel. And here is the delta itself. It's smaller, more northerly side, and it's larger southerly side. And of course, you can see where wave base is here. This image shows us where we have clear water versus where there's sand and suspension. And of course, that sand and suspension is showing us where waves were feeling the bottom along here. And so the delta, the front of it is essentially through here, where the sand is being distributed. And then we get farther out here, and that's the pro-delta. So all of those studies that I just showed you were about the sand distribution. The asymmetric delta, the individually dated ridges along shore here, each of those are about sand. So what about clay? Like many geologists worldwide, a lot of the initial studies come in and focus on sand. And if we're thinking about reservoirs, that's great. If we're thinking about preservation of deltas, that's great. But in a larger context, we need to know the whole system. We need to know about seals. We need to know about flow barriers and we need to understand the overall volume of sediment that is being deposited in this system. And all three of these earlier studies that I just showed you were up here about that sand. And the clay is being left out of the discussion. And so that's what we set out to study here. So there are two primary sources of clays for this river. The Brazos River has this red clay that you can see in the satellite image and highlighted in arrows in case you can't. But this red clay that comes out of the Brazos River is usually very obvious. The Brazos River has, as I said before, the highest suspended sediment load in Texas, and it's carrying this suspended clay all the way out into the Gulf. And at the same time, we have a great deal of longshore transported clay. This longshore clay largely comes from the Mississippi River. The Mississippi is so large, it really dominates the signal for much of the Gulf. And any of those smaller rivers between the Brazos and the Mississippi are not really being recorded here. The Brazos clay is typically red, and the other clay is typically gray. If we sort of separate that into two different sources now, and we're going to call clay source number 1 our longshore transported clay, coming across from the Mississippi, across Louisiana, and down towards central Texas. This longshore transported clay from the Mississippi is dominantly smectite. Smectite looks gray like this in the water column. Our source number 2 of clay in this river is dominantly illite and also some kaolinite. The central Texas is characterized by these Triassic red beds, and that's where the Brazos River is flowing through Texas, picking up this Triassic clay and bringing it out to the Gulf. And in these two pictures of the river and here of the delta mouth, we can see this very distinct color of this red clay entering the water. And that's largely illite from the Brazos. If we look at the cores, and I showed you there were 20 cores collected in the Pro-Delta area, these individual clays remain identifiable in the core. And so here we can see these gray bands, these individual illite rich bands. And then in the red, we have what's usually coming out of the Brazos itself. So if we look at these different segments where we have downdrift, and again, by drift, we're thinking about the dominant longshore drift, which comes from the northeast down towards the southwest across the Texas shelf. So from Mississippi to Houston to Brazos to Corpus and so forth. And we'll lump these cores into a downdrift set and an updrift set of cores. We can see a few different images here. And right here is, I think, where you should be surprised. Maybe if you're a Texas geologist or a regular kayaker on the Texas coast, or just a Holocene sedimentologist, and everything I said, you sort of said, yeah, I know. This is the slide where it's a shock. What we see here is the downdrift clays, and we see largely this red to gray colors, so our Brazos to our Mississippi, but it's gradational, it's mixed, and we don't see clear banding. On the other hand, if you look at the updrift cores, So where we are updrift, up in the longshore drift current, we see very distinct boundaries between Brazos clays and gray clays from the Mississippi. Brazos and then Mississippi. And this is really exactly different than the model that we put forth. And a good reminder of why we often need to go in and do the details of the research program rather than just go in with our assumed models. So besides just looking at color, of course, we did more work than that. We did a range of detailed grain size measurements. We do laser particle size analysis, like many people do. I run a Silas, which has 3 individual lasers in it, allowing us to do from about 0.2 microns to 2.5 millimeters in very detailed grain size analyses. What that shows us here is that actually in the red star here, red here, so the Brazos sediments are largely usually around 3 microns. The longshore drift sediments are actually coarser than that. They're coming from farther away, but they are much coarser, around a 9 micron mean. Of course, it's easy to keep anything those sizes in suspension, so that doesn't really mean much, but it means we can differentiate based on size as well as color. And then if we look at some XRD of those individual facies, we can see that in the Brazos clays, we have virtually no smectite, dominantly illite, and of course there's quartz and everything. And if we think then about the gray clays, they are smectite rich, as well as having some illite and kaolinite in there. And then we made maps of how these facies get distributed across the shelf. We identified pure Brazos mud, pure Mississippi mud, mixed systems, and then of course we identified the silt and sand facies. And you can see those silt and sand facies, of course, are largely in front of the river. They're coming out and being in the main portion of the delta. And so looking at some cross sections very quickly, just a dip section, and we can get used to the colors here in this sort of, orange and gold. We can see the silt and sand. They are, of course, largely onshore and then disappearing largely as we move offshore into the pro-delta. And then the different mud facies where we have pure Brazos or we have pure Mississippi versus the medium in between. We can see that there's no distinct changes through here in mud. That's going to show up in our strike section. And here is a strike section looking at these cores. So we have water depth here, again, going from sea level down to starting at about 12 meters is our deepest core for water. And then the cores go down from there. And then here we can see the silt and sand is still showing up quite clearly in the downdrift side. Updrift, there's virtually no silt and sand out here in the pro-delta. But here we get the mixed mud, and here we get the individual layers of mud. So longshore drift isn't actually always the same. When we talk about longshore drift being dominantly from the northeast to the southwest, that is dominant, but that only means it's around 60% of the time or so. So for this period of 1993 to 2008, we can look at 36 months that were clearly normal, but 26 that were reversed. And then there's some times in the middle where it's a little bit more variable. So here's the model I'm going to put forward to you for how the pro-delta formed. Starting with time 1 in the upper panel here, moving through time 3A, and then across the second row and through the bottom row. During a normal time, we have normal longshore drift. We have normal transport from the river of sediments out into the Gulf, and we have normal longshore drift moving that plume of clays out downdrift. As flooding proceeds, we get this plume of sediment coming down the Brazos River. And at the same time, because the river is not responding all alone, it is at the same time moving, at the same time it's going to flood stage, we're also getting waves and winds and the reversal of the longshore drift. This new plume of Brazos sediment is actually ending up in this reversed position. And then you can see that through time, we get this alternation. In each of these, the darker color is the current phase, and then this grayed out part is what's already been deposited. And so that we alternate over time and end up with a series of sediments where we have the mixing, the ongoing everyday river, everyday longshore drift leads to this clays being mixed down here. But the distinct pulses are only occurring when we have the flooding, which happens to go along with the reversed longshore. So how does this fit into the broader context? I mentioned in the third paper that studied the Brazos before us, indicated that those individual ridges in the delta appear to be tied to episodic events. Those episodic events are actually the El Nino cycle. So of course, El Nino happens around the world and it has very different characteristics depending on where you are. In Texas, the El Nino is a flood event. It's a very rainfall rich event, and it occurs every 3 to 7 years. Each of those pulses of sediment is bringing out a new sandbar, and we think that it's also bringing out a new distinct environment in the pro-delta as well. So here what we have is this updrift core, has in this particular one 16 of these high discharge flood distinct pulses, indicating that we have a reversal of longshore drift and a flood in the river. So we think we can now tie the pro-delta to the sandy part onshore. So to conclude this section of the talk, we've got thicker and more uniform deposits of the Brazos pro-delta actually in the updrift environment. This correlates with a reversal of longshore drift during northerlies and river flood episodes, maybe with El Ninos. At the same time, more mixing of facies is found in the downdrift environment because this is the more continuous deposition through history rather than just individual flood events. Did you say something there, Susan?
Not yet.
Okay. So now in my last couple of minutes, I'm just going to show you a sneak peek at our newest work where we're studying another delta. So this is just an example of a different type of spot and what we would see if we were in the field. San Luis Pass shown here is a tidal delta. So this is Galveston Island here. This is Follett's Island here, the Gulf of Mexico out here. And this is the part of Galveston Bay called West Bay. And here you can see this just classic tidal delta right there. It is the only truly natural tidal delta in Texas. We've taken a series of sediment samples, as I showed you in the methods section. We walk around out there. We take sediment samples on the lee and stoss side of ripples, and then study each of these individual ripples and how they move downstream along the bar. We tie that to water depth. We tie that to water velocity. Note, we do not wade out here during field trips. This part of the Gulf actually has very strong currents through here. There's actually often drownings here when fishermen get caught off guard by the tidal flow here. So during our field trip, we're actually up on this side here, not this side out here. And we compare that grain size, the water velocity, the depth to the bed forms that we are observing and studying the ripples and the dunes. Again, we do laser particle size analysis on all of those sediments. Here you can very distinctly see the drop off where we go from largely sand here on the shallow water, and then as soon as we step into the deeper water, the pro delta, that sand signature is gone. You can almost map the delta front just by looking at our grain size pie charts there. And this is some very classic images on how we think about water depth and dune heights. So this is, again, very classic sedimentology paper, Allen, 1982. And we've just added the colors to make it a little easier for you to see these old figures while still using the classics. And what you can see is that there are very distinct ways that we have a relationship between water depth and dune height, where here in green and yellow, we have tidal examples from around the world. And then blue and red, we have river examples from around the world. These other examples are marine. These types of relationships are what geologists working in the subsurface use to interpret if something was tidal or river or marine. These figures, these compilations are used to say, oh, well, I've got a core with some ripples and I've got these ripples and this bar height, therefore it must be a river or it must be tidal. Except here's our San Luis Pass tidal delta plotted right in here in the river zone. So that if we look at our water depth, our microtidal environment, our grain size, it's plotting here as though it would be a river. So again, I said this was just a sneak peek. This is our newest work. It's in review right now. And what we can say is that there is much greater variability than these classic models suggest. And it's a cautionary tale for using simple analogs for working in the subsurface without getting all of the details included. So I'll leave it at that, take questions, and say thank you to listening. Okay.
Excellent, thank you, Julia. We're starting to receive questions already. I'd like to remind our audience you're muted, but you can ask questions using the questions box in the GoToWebinar feature. And let me start with some of these questions that are coming in. What are smear slides?
Oh, okay. A smear slide is usually used for looking at sediment that's not fully lithified, and it's a way of putting some of the sediment onto a microscope slide. But unlike if you were looking at rock or something that had been fully lithified and cut with a saw, a smear slide usually you make with a toothpick and just smear some of the sediments onto a slide and cure it with UV light, a couple extra steps in there with epoxy. but it's essentially a thin section of loose sediment.
Thank you. Okay, the next question has several parts. What is the role of hypernickel flows during the Brazos River flood events? More oriented updrift or downdrift? What is the role of El Nino, and could this be a mechanism for delivering red clays updrift?
Okay, so I think what you said is, what is the role of hyperpycnal flows? And that's a really good question, because Brazos is an interesting river that does have very distinct hyperpycnal flows. You're absolutely right, whoever answered that question or asked that question. So what's going to control hyperpycnal flows in Brazos or anywhere else, of course, is the water salinity, the water temperature, and the sediment loading. What we have in the Brazos is a river and a body of water that don't change salinity a whole lot and don't change temperature a whole lot. They're not particularly seasonal for temperature or salinity. And so what does change in the Brazos is the sediment load. And that's going to drive the density differences between the fluvial water and the basin water. There is another scientist at Texas A&M Galveston who has done some interesting studies on changes of hyperpycnal flows, or sort of the episodic nature of hyperpycnal flows in the Brazos River itself, Tim Del Pena. And I don't know exactly what they have observed and how that ties to El Nino or individual sediment loads. So what I can just say is, yes, it changes a lot based on the current conditions. In general, and the last part there was, how does that control the distribution of the sediment?
Right.
It's still going to follow that model I have, whether it's entering in as a hyperpycnal flow or not. It's still following that pattern of being reworked only at certain times. Thank you.
Okay, the next question, the questioner thinks it refers to slide 12, perhaps. And he asks, in general, can you talk on any types of faulting?
Like I was trying to go to slide 12. I'm struggling to change slides, but there are no significant faulting at this time scale. What I can say is that if we're looking even at the Holocene, I'm talking here about 100 years, but on this figure, yeah, there's some faulting in there, but that's showing you back in the thousands of years. There is some gross faulting there, and that's what's visible on this seismic line. And so there is some very limited gross faulting that does sort of help, get the thicker and thicker packages in some places. It's not going to fundamentally change the distribution of sediments in a late Pleistocene scale, and certainly not in a Holocene to modern scale.
Thank you. The next question is, why are updrift smectite grains larger than downdrift clays?
Yeah, that's a really good question. And again, one of those surprises to us. I mentioned, I think, that in general, even at 9 microns, that's plenty small to stay in suspension. Even once of course, clays flock together once they hit the salt water. So when they're in the fluvial water, the fresh water, they never get deposited. And that's why the sand might be deposited in the fluvial system, but we don't see these clays really at all in the river deposits. But once they reach the salt water, they start to flock. They can be deposited, but at 9 microns, that is still plenty small to stay in suspension. And that is the size of an individual mineral particle, not of a flock. And my understanding from talking to clay mineralogists is that those differences actually have to do with sort of standard ways that the different clay minerals erode from their parent rock, and would often be found that the different clays tend to have different site signatures. It becomes significant to us because it gives us a quick and dirty way, besides color, to say which mineral we have. If we say we have this grain size peak at 3, well, then we can be pretty sure it's illite.
What is the rate of sedimentation? Yes, what is the rate of sedimentation in the modern delta?
Well, it's a lot lower. And this is something that's proven really interesting to me, and I think might be our next project. I mentioned that from around 1930 till around 2000, the modern Brazos Delta actually grew very quickly. And it did so because it was cannibalizing the pre-1929 Delta. And so it grew much faster than it really could because it had this extra sediment source updrift. Once that sediment updrift was removed, the rate of growth slowed, and now the Brazos Delta is actually eroding, at least along the shoreline. It's being eroded very quickly now. It actually has become, in the last 5 years or so, it's becoming harder and harder for me to take field trips there because the beach is being eaten away. And of course, we know sea level is rising. And so the rate of growth, rate of sedimentation in that delta is not found its sort of equilibrium point yet. It went through this very fast phase, and now it's eroding to make up for it. And somewhere in the next several decades, I think we'll find exactly where it's meant to be.
Thank you. We're nearing the end of our time, so I'm going to ask one last question, but I want to let all the other people know who have asked questions in the chat that we do have those recorded, and we'll make sure you get responses to those questions offline. Later today, you'll receive a link to a recording of today's webinar and evaluation form, a link to the registration details for Julia Weltner's class on modern coastal systems of Texas. Okay, so here's your last question. Can you describe how these analogs specifically help geologists understand Texas Gulf Coast reservoirs?
Let me start by saying I hope they do more than that. I hope they don't just teach you about Texas reservoirs. I think they should be teaching us in general about deltas or barrier islands or tidal systems, and understanding some of the variability within those systems. So if we focus on the Brazos in general, the Brazos, traditionally was classified as a wave-dominated delta. And, if you fly over it in an airplane, of course, that's what it looks like, is a wave-dominated delta, not tidal, not fluvial, it's not a bird's foot. But now that we work there, we can tell you so much more about it. It's got these pulse systems where it's getting a pulse of sand and then a pulse of mud and then a pulse of sand, and that's controlled by floods in the drainage basin itself. The distribution of clays is controlled by alternating longshore currents. The overall geometry is also controlled by an interplay between those things. And so somebody who was looking for just a wave-dominated delta and wanted everything to just be nice wave-sorted sands would be awfully disappointed in the Brazos. On the other hand, by knowing its details, maybe we can make more use of it. So I'm not trying to provide an analog for the Wilcox or something else specifically in Texas, but rather a broad understanding of the details of how sediments get distributed, and therefore, how that might relate to permeability or connectivity somewhere. Thank you for the
Excellent.
questions. Those were great comments and questions. I appreciate it.
Thanks very much. Thanks to all our listeners today. Thanks for tuning in to this talk about the Upper Texas Gulf Coast as reservoir analogs, and we look forward to seeing you at our next webinar in May. Goodbye.
Thank you. Bye.
Bye.